Welcome back. Today we're going to investigate the rational to the real to the complex. So far we've been talking about polynomials or many numbers, how to multiply and divide them, and putting it all together to create a general division algorithm. Today we're going to start applying that general division algorithm to dividing by the binomial. So opening up to 2.4 on page 26, please make sure that you have an erasable pen or pencil, and let's get to work. Looking at example 1, find the following quotients and write the quotient in standard form. So let's see, if I have x divided minus 3 going into x squared, put in my placeholder for the x value, minus 9. How many times does x go into x squared? Well, that's x. So that's x squared minus 3x. When I subtract it off, that of course becomes plus 3x. So because minus minus is plus, bring down the 9. How many times does x go into 3x? Why, 3 times in fact. 3x minus 9, left over is 0. How very convenient. And in fact, if I wanted to, I could have noticed that this was actually just a difference of squared problem. The numerator would factor to x minus 3, x plus 3. The denominator is x minus 3, and any number divided by itself is 1. This is a really good way to cross-check any of your division. Now, similarly, I can do the same process. Hit pause, check back with me in a minute to see what your quotient is for number 2. Notice, make sure you put your placeholders in for the 2 missing terms. Notice, as I multiply it, this following term seems to get larger and larger. So in my last term, I have to multiply by, let's see, that's 9x, bring down the 27. So multiply 9 times 27, and a remainder of 0. So x to the third minus 27 divided by x minus 3 equals x squared plus 3x plus 9. Now notice, let's actually put those answers on top of each other. Right here, if we have x plus 3, then x squared plus 3x plus 9. Now any 2 points make a line, so if we want to really understand the problem, we should definitely do the third point to see if it actually continues the pattern. You may need to do this on a separate piece of paper. So hit pause, try this out on a separate piece of paper with me. Here we go. X minus 3 going into x to the fourth, putting our placeholders for the squares, thirds, x's, and then minus 81 at the end. So therefore, this goes in x to the third time. So altogether, when we go through this entire process, each time increasing by a power of 3, our quotient is x to the third plus 3x squared plus 9x plus 27. When we compare that to the solutions to the other 3, we begin to notice a pattern. First of all, the powers of x's are increasing. Secondly, the coefficients are also increasing. So there's 1, 1, 1, 3, 3, 3, 9, 9, 27. Use the patterns to predict each of the following quotients. Explain how you arrived at your prediction, and then test it by applying the reverse tabular method to the long division. So here, A exactly echoes 1. Do you see how these have the same structure, except here this is 3 squared and here this is 12 squared. So my prediction here would be that the solution would be x equals 12. And then just for the sake of changing it up, since we use long division for this, let's do this by reverse tabular. So that means one dimension is going to be x minus 12, and the result has to be x squared 0x is minus 144. So let's see, it has to be an x times an x to get you x squared, which means that right there. And then x times negative 12 would be negative 12x here. So this also had to be, to make this add to 0, had to be a 12x. But rather positive 12x, which means then negative 12 times positive 12 is negative 144, resulting in this, which means this checks out. If I then in turn look at what this means as a general pattern, I can begin to think about the following. Notice what happens with difference of squares. If I have x, which equals x squared, and 144 times 4 squared, so sorry, there's supposed to be a equal sign there. Apologize for the typo. Then when I look at a difference of squares, that's the same as x squared minus 4 squared, or x plus 4 times x minus 4. When you have two numbers, once being added, the other being subtracted, they're known as conjugates. Another example of conjugates would be 3a plus 5 and 3a minus 5. The same terms, but one's a sum and one's a difference. Now, based on this, the quotient of x squared minus a squared, if it follows the same pattern as what we've been observing so far, ought to be x plus a. Use the reverse tabular method or long division, whichever you prefer. So again, I'm going to try the reverse tabular method, just because it's not the one that I'm as familiar with. So my quotient goes on the outside, x squared, 0x, notice I have a placeholder, minus a squared. And at each term I draw my line. Then x minus a, which I'm divided by. So in order to get x squared, well, that has to be x. So that's x squared. And if this is x times negative a, this is negative ax. If this needs to add to equal 0, that has to be positive ax. That makes this positive a, which makes this negative a squared, which checks out. Now, here's where it starts to get fun. Look at all these multiplications. These are multiplications you've known how to do since 6th grade or maybe 7th grade, whenever they taught you to do double digits. But what if we were to do these in a very different way? Like, what instead of saying this was 6 times 8, I said this was 7 minus 1 times 7 plus 1. Before you go yell at me saying, Mrs. Carl, why do I have to do things in a new and complicated way? Remember, whenever we learn a new technique, we try it on something we know to make sure that it can help us with something more complicated that we don't know. And notice what happens here. This is the average of the products. That's not an accident. 6 is 1 less than 7, and 8 is 1 more than 7. Both of these products, there's a distance from each of the terms. So it's pretty easy to see this one intuitively, and if we go ahead and then think about this as a product of squares, well, that's going to be 49 minus 1, or 48. Now, for someone like me who has a really hard time remembering the 8 times tables, especially 6 times 8 and 7 times 8, because, I don't know, they just don't stick in my head, this process can actually be really useful. Now, let's take something that's a little less immediately intuitive. What if I'm multiplying 11 and 19, and I want to write it again as a difference of squares? So I need to have a sum and a difference, which the same leading in the same difference. So to find the middle number between the two, I have to find the average. So that's 11 plus 19 divided by 2, which is going to be, let's see, 30 divided by 2, or 15. So 15. And 15 plus 4 gives me 19, and 15 minus 4 gives me 11. Isn't that neat how it works out so exactly? So therefore, to compute 11 times 19, I would have 15 squared minus 16, or 4 squared. Now what that is, well, since 15 squared is 225, it's 225 minus 16, or since it's close enough to 225 minus 15 minus 1, because I hate carrying, that right there is going to be, let's see, 210 minus 1, or 209. We can do the similar thing with C and D. Hit a moment, hit pause, see if you can guess how you would set this up, and check back with me. Now, usually 23 times 17 is no fun because there's no rational pattern to it. But if we think of 23 times 17 as 20 plus 3 times 20 minus 3, notice 20 is the average of 23 and 17, plus 3 is how far away both numbers are from the average. What's called the spread is the same thing as 20 squared, or 400, minus 9. Now that I can do in my head. 400 minus 9, well, that's just 391. And there's a number where I'm very grateful I don't have to do any carrying or like complicated stuff. Let's look at another one. Now here, right here, this is actually 34 and 26. Again, not very friendly numbers. But if we average the two, 34 plus 26 divided by 2, something very interesting starts to happen. Let's see. The average of the two is 30. So 30 plus something, 30 minus something. Well, that's 30 plus 4, 30 minus 4. 30 squared is really easy to compute. That's just 900. 900 minus 16. 900 minus 16, well, 900 minus 10 is 890 minus 6. Well, that's easier. That's 884. A really pesky and annoying multiplication requires no borrowing, no moving, no etc. You just go ahead and do it. In class tomorrow, we're actually going to even do fairly complicated ones, like, for example, 993 times 1007, finding very quickly how to do very large and complicated multiplications using this type of technique. Looking forward to playing with these with you in class tomorrow. I'll see you then. Checking out, Mrs. Carl.